Good morning, everybody. My name is Nicolas, and I'm employed at JP Morgan, where we work very hard at making very simple things appear to be very complicated. Now, you might be thinking, stage fright has gotten to me. I must have said that sentence the wrong way around. No, I haven't, and you clearly have never worked in finance. I'm here today because I want to talk to you about free, which is a subject of some fascination for me. Couldn't tell you why. We all have our little quirks. But I have been trying and failing to learn it for quite a while now. And I think it was in my 7th failed attempt that a friend of mine, known to be particularly fond of pithy statements, came to me and told me, Nicolas, free is very simple. It is merely the defunctionalization of a monad in its most cumbersome shape. He didn't add, so what's the problem? But it was clearly implied. So, the weird thing about that is, this is actually what I needed to hear for the whole concept of free-to-click. Turns out, it's one of these concepts that is very simple, but people make out to be very complicated. People who presumably work in finance. And the goal of this talk is going to be to explain that statement, because it is one of these statements that functional programmers are quite fond of, isn't it? If you know what free is, then that definition is beautiful. It's clear, it's concise, it's clever, perfect. If you don't know what it is, though, it couldn't possibly be any less helpful. I do have a colleague who gave that a valiant shot a couple of months ago, but still the worst possible explanation if you don't understand what it is. What you'll get out of this talk, then, is I'm going to explain that statement, I'm going to explain what free is, I'm going to explain when to use it and how to use it. Not to spoil the ending, though. It's very much one of these talks where the journey matters a lot more than the destination, because understanding free is cool and all, and it's going to allow you to shine at parties like the one we had yesterday, for example. But what you're really going to get out of this talk is the concept, the techniques, and the notions that we will build along the way. And in order to show you all that, I'm going to use the extremely traditional example of a simple console DSL. What we're going to try to do is that. So I apologize. This is not centered. It was supposed to be, but I'm not going to spend 10 minutes fiddling with that, because I might run a little over time. So we're going to have to accept that for the moment. What we want to do is to write this program, read the user's name, ask users for the name, read the name, and then grid them by name. So that looks pretty straightforward, but I'm going to add one wrinkle. I want that program to be written as a value so that I can write multiple interpreters for it. And if you're not sold on the concept of program as values, I'm going to have to ask you to suspend your disbelief for the next, let's say, 35 minutes or so. Because, yeah, one thing is important to know about me. I'm an absolute idiot. I knew that Scalar was a 30 minutes kind of talk conference. I forgot, and I wrote a 45 minutes kind of talk. Margot is very upset with me. I've done my best. No, she says that, but if my body disappears, you know it's her. So I've trimmed it down to about 35 minutes. I'm going to run over time, especially if I keep ad-libbing perfectly useless content like I'm doing right now, so let's crack on. A solution to representing that is, it's well known. You use an algebraic data type, console, with two variants. The first one, print, and the second one, read. Straightforward, nothing too surprising, and the evaluation function is going to be, well, it's going to be very straightforward. We have a sum type here, so we're going to have to deconstruct it via pattern matching. And then we have to provide an implementation for both branches. The first branch is going to be print, and the second branch is going to be read. Nothing too surprising here, but there is a bit of a problem. What do you think the type of this thing is? Can anybody tell me? Okay. Well, print evaluates to unit. Readline evaluates to string. And both these types evaluate to any, which is never a good type to manipulate. So we're going to want to fix that. And again, the fix for that specific problem is very well known. You just make console polymorphic. You add a type parameter whose job is to represent the value that you would have, the type of the values that you would have as you evaluate a statement. So in the case of print, for example, that's going to be console of unit because print returns a unit. And in the case of read, you get a string because read evaluates to a string. Which solves our problem here immediately because once we add the type parameter, the very definition of that type parameter is that's going to be the return type of eval, so we just have to do that. And that is going to compile, that's going to run, and everything's going to be fine. So quick break, because we've done a first step into understanding this whole thing. What we've learned. We have learned first that console statements are encoded as, I say generalized algebraic data types, you can just think of it as algebraic data types that are polymorphic, that's close enough. We know how to evaluate them. We know how to evaluate a single statement simply by pattern matching on it. But we have not solved our problem, though, have we? Our problem was to chain statements, which we've not done at all. We just have the one statement. So how would we chain them? How would we represent a sequence of statements? Well, what we're going to do is we're going to do the obvious naive implementation that this statement suggests, a sequence of statements. We're going to write a program as a list of statements. So the first statement is going to be a print statement. Then we're going to const that into read, and then onto another print, and then we need the marker for the end of the list. We've not solved the problem at all, though. Can anybody see what the problem is here? It's going to compile and run. Here's a hint. We were supposed to greet user by name. We are not greeting them by name at all. So we have not solved the problem at all. We feel like we might have, but we've done half of the job only. And the problem here is that there is no link between read and print. There's no way for read to pass any information to print. The link exists, but it's here, between the two const cells. So what we want to do is to bring that link up there down into read. So really, that means we want to have a new field there, which represents the next statement in the chain. And since now read is going to be evaluated, and then we're going to evaluate the next statement in the chain, then we don't want a string here, because that's going to evaluate to an A. Similarly, we want to bring down that link to print. So print is going to have a next statement as well, and similarly, it's going to become a console of A. And of course, we need the marker for the end of the chain of commands. So I'm going to call it stop. I'm not super excited about that. It's an implementation detail that has bubbled up to the public API. It wasn't part of the specification. It's not part of the problem we're trying to solve, but sometimes software development is like that. You have to take one step backwards in order to take two forwards. So let's play along with that for the moment. So we have our type. We can simplify it slightly more, because in Scalar, if a variant, the extends clause of a variant is exactly the same as the actual sum type, then you can get rid of it. So that's our data type. Not as terse as I'd like it to be, but at least it's working for us. And now we're going to have to fix program, aren't we? Very easy. We know that nil is now called stop. And then all these constants to the right, this is why I presented it that way. I know it's not traditional to present this like in Scala, but it makes for a very easy way to fix a program. You just replace all of these by commas. And you get this program, which feels like a step forward, but we're still not greeting the user by name, are we? So we're not quite done yet. And the idea here is print is created before read has even had a chance to read from standard input, isn't it? So this can't possibly work, because read, while it knows about the next statement, because it has this next field, read cannot pass that information to the next statement. All that is a very long-winded way of saying this is a wrong type. We don't want next to be a console. We want it to be a function that, given the string that we have read, return the console. That is known as a continuation. So we're doing continuation passing style here. And for the sake of consistency, and also because otherwise it wouldn't work, but that's too complicated to explain, we are going to use a continuation here as well. So now it's all continuation passing style, which is absolutely awful, but this is what we have for the moment. That works. We are now going to need to fix the program one last time. Even easier than before. Function with a string. Finally, we can greet the user by name. And we end with a function. And that compile, that works, it is brilliant, but we do need to fix the evaluation, don't we? First, fix the variants. Print and read now have a next field. Second, and this is an important technique, at least if you're a speaker, I'm going to introduce you to the concept of programming via diagrams. It's not super useful when you're actually writing code. It's a lot of work. You have no idea how long it took me to write these. But as a visual aid in a conference, it's much, much more understandable than code. So let me show you how that works. we start from the type that we have here with print line return unit. So we go from unit, and we want to get to an A, the return type as a function. And then we just try to go from one to the other. So what do we have? Well, we have next, don't we? Which takes us to a console of A. And now we need to go from a console of A to an A. Can anybody see what function we could use for that? Somebody said something, but I couldn't quite get it. I'm going to pretend that you said eval, and you're absolutely right. Very well done. Eval goes from a console of A to an A. And yes, that does make eval recursive. But that makes sense, doesn't it? Because, well, console is a recursive data type, so obviously you need a recursive solution to a recursive problem. So that makes sense. And then once you have joined the dots like that, that's your solution clear as day. You just have to follow the arrows. Of course, function composition is weird, so you follow them the other way around, which is confusing, but that's just math. So this is our implementation. We're going to do the exact same thing for the other one. Read line, we start from a string, want to get to an A, and we have next and eval, and that gives us our implementation. Done. We can now evaluate our chains of statement. So we just, of course, need to add the stop case, which just evaluates to unit. What we have learned so far is chaining console statement is done by continuations, which is not nice, but it works, because we have solved our problem, haven't we? We know that evaluating a chain of statement is a recursive pattern match, no big surprise, recursive subtypes, recursive pattern match, obviously. The one thing that I'm very disappointed in here is this is not very composable, is it? Once you have a console, you're done. You have your console, but you can't really compose consoles together. And the essence of good software craftsmanship is to make composable APIs so that you provide simple solutions to simple problems and allow people to combine them together, combine atomic statements into molecular solutions, larger and larger solutions. So we're going to try to do that, because this is not very reusable. The way we're going to do that is by, well, we have a program already, right, which is already composed. So what I'm going to do is I'm going to decompose that and then see where that takes us. And once we're done with decomposing it, we're going to recompose it and try to make that work properly. How is that going to work? Well, this is just a copy and paste from the previous slides. This is what we have, and at least to me, there's an obvious two parts to that program. The first one being this. We ask a user for the name, and then we read it. So I'm going to extract that to ask here, which that's not going to compile. Obviously, that's not the right type, but that's roughly the shape of what I want. I want somehow to return the name that I have read, right? And the type of that is going to be something console, which eventually yields a string. So it should look like that. This is ideally what we want to have. No, it doesn't compile. We'll fix that, don't worry. And then we have the second part, this, which, given a name, greets the user by their name. So that's going to be this bit of code I'm just copying and pasting and calling greet. And that is a function that takes a string, returns a console, that eventually evaluates to a unit. So that's going to be a string to console of unit. Now, as I said, this, well, we can get rid of program, because the entire point is not to have it and then recompose it later. So I can get rid of that. And now the compiler is going to complain about that, because the continuation in read returns a console and not a string. So the compiler is not happy about that at all. There's two ways we could fix that. The first one would be to think really hard about what it means to interrupt a series of continuation in the middle. Think really, really very hard. It takes a while to get it, and when you do get it, you take the obvious solution. But it's a lot of work. I'm quite lazy. So what I do is, the compiler is telling me, right, you return a string, but you said it had to be a console, so one of these two's got to give. Well, I wanted to return a string, so what's going to have to give is that bit here. I'm no longer returning a console of A, but an A, which makes sense, again, because we want to be able to interrupt a sequence of console statements, don't we? So if we want to be able to interrupt it, we have to be able to say, this is the end, and that's not a console. So that works. And, well, that allows us, sort of forgot what I wanted to say here. Right, yes, no, I do. We have a console, it returns a console, which returns a string. So that causes this type to become a console of string. Not a super comfortable type. Some of you might be familiar with fix. Clearly, we headed that way. We also, that's a good news, we don't need stop any longer, do we? Because we had stop in order to say, stop here, return unit. Well, in order to do that now, what we can do instead is return unit. We don't need stop any longer. which is brilliant, and we can get rid of it. We're going to have to fix the evaluation, because we don't have the stop statement any longer. And then, well, we have a problem, don't we? Because eval takes a console of A, but next now returns an A. So that's not going to compile. Luckily enough, next returns an A, which is what eval needs. So we can just get rid of eval here and make eval now non-recursive. It just evaluates a single console statement. How do we chain console statements now? Because we've broken that thing, right? We can evaluate single statements, but not chains. What we want to do is say, well, there's two cases, really. Whatever is returned by the next statement is either a console or it's not. If it is a console, then I keep evaluating. And if it is a console, if it is not a console, then I've reached the end of my program, and I can just return that instead. We could probably do that with runtime introspection. We've not been raised in a pigsty, so we're not going to do that. This slide shows exactly this duality here. We have, in one case, a console of string, in the other case, a unit. It's one or the other. That should be, at least, obviously, a sum type, which I'm going to call chain, because it's going to be chain statements. Chains has two variants. So the first one, done, which represents my program is done. Here's the A that I found. Use it. And my second branch is going to be next, which represents a case where it's not a value that we have, it's another console to evaluate. There's a bit of a tricky bit here. Instinctively, what do you want to put there in that type? You want to put A, right? I mean, I certainly did. But if you think about it, that doesn't work, because if you have a console of A, that means that console is going to return a value and stop there. And we want an arbitrarily deep chain of statements. So what you need here is a chain of A. And if that type next looks very, very familiar to you because you have, in fact, studied fix, that is not at all a coincidence. OK, we have chain. We're going to have to evaluate it. We're going to use programming by diagrams again. We have a chain of A. That's a sum type, so we're going to deconstruct it. The first branch, we have an A, want an A, literally nothing to do. We can just return that. Easy enough. Second case, we have console of chain of A, want to get to an A, and we have eval chain, which is going to link that bit, so we need to go from a console of chain of A to chain of A. Does anybody know of a type of a function that would solve that? Well, actually, no, almost, but not quite. Think about it this way. Pretend that chain of A, hang on, how do I want to say that? Yeah, pretend that chain of A is X. So you go from a console of X to an X. You're not going to use eval chain, which doesn't have the right type, but you're going to use in your own time. Oh, that's fun. I'm going to have to hide here now, because apparently my clicker is not working any longer. We're going to have to use eval, right? Which makes sense, doesn't it? It really makes sense that when you're going to evaluate a chain of statements, then you're going to need to know how to evaluate a single statement. So it makes sense that we're going to use eval to evaluate a chain of statements. And so the solution is very trivial. We just follow the arrows and get to that, which allows us now that everything works to fix this program. First thing, we are now, since those are chain statements, we are going to be using the chain type, which is much nicer, isn't it? That's a lot better than what we had. It's about to get a lot worse, because now all of the final values need to be wrapped in a done, and all of the intermediate value needs to be wrapped in a next. That is dreadful, and we're going to have to do something about it, because we do not want to be right in that. I mean, we just have, but we're going to try and not have to do it again in the future. What we've learned so far, yeah, maybe 40 minutes. What we've learned so far is we now have a specific type for chain statements and console statements. And we know how to evaluate both single and chain console statements, which is brilliant. We have solved our problems, and we managed to compose everything. Now let's see about composing, and this is when we start using scary words like MONAD. How are we going to compose program? Well, let's see, we have that. We have ask, which is a chain of string, and greet, which is this function. And we want to write program, which is a chain of unit. It's a chain of statements that ultimately evaluates to a unit, isn't it? So let's look at that as a diagram. We have a chain of string, want to get to a chain of unit, and we have a string to chain of unit. Now, in these diagrams, whenever you see a sort of triangular shape like that, That means something flat mappy is going on, something monadic is going on. Here, obviously, think about it. You have a chain of something, you have a function from something to chain of something else, and you want a chain of something else. That's a direct call to flat map. So we'd really like to be able to write that. Obviously, we can't. Chain is not a monad, so we're going to have to fix that. And the way we fix that is by declaring a monad instance for chain. And there's two ways of declaring a monad instance. You could use, there's two different main configurations, and this is one of them, the one where you declare monad by flatten and pure, and you have a constraint on it being a functor, which I've just made it map here because I only have so much screen real estate. But that's really flatten, pure, dependency on functor. That is also known as the most cumbersome shape of a monad because you have so much stuff to write, whereas the other one, flat map and pure, is much easier. So maybe we're starting to get an idea of what that initial statement in the beginning meant. So let's implement all these things. This is where programming with diagrams is really, really going to prove its worth. Let's start with pure. That one is simple. We have an A. We want to get to a chain of A. That is exactly done. Done takes an A, lifts it into an A. So this is easy. Done. We can just fix it and then map. That's going to be the most difficult diagrams of the entire talk, so if you have to pay attention now. We have a chain of A, which is obviously a sum type, so we're going to deconstruct it. The first part is easy enough. We have an A, we want to get to a chain of B. We have a function from A to B, so we want to link a B to a chain of B. And we've just done that, haven't we? That would be done. So that's easy enough. Now, fix the code. The whole screen is going to move because the next diagram is going to be massive. So the code is going to go a lot lower. It's not changing, so I'm not cheating here. But there we go, leaving myself a lot of room. We have a console of chain of A, we want to get to a chain of B, and we have a function from A to B. What we also have, this being a recursive problem, is probably going to have a recursive solution. What we also have is map. And if you look at map a certain way, kind of a Haskell-y kind of way, you can think of it as a function, taking a function from A to B and returning a function from chain of A to chain of B. And that rectangular shape here is very important. You know how the triangles means flat map is going on somewhere? That means functor is going on somewhere. We have a functor. And yes, obviously, we said chain was going to be a monad. So if it's a monad, it's a functor. So we can lift that. But remember, if you see a rectangular shape like that, look for a functor somewhere. And I'm going to cheat a little here, because I know I'm going to need that function, and I don't want to spend another 10 minutes justifying it. So I'm just putting that in here. And once we have that, well, what do we have here? Well, that looks a lot like a rectangle, doesn't it? So that looks like we might be wanting to do something mappy. We want to be doing that. Lift that function at the bottom into console. In order to do that, though, we would need for console to be a functor. I'm just going to leave that as a goal that we're going to discharge a bit later. Obviously, console is a functor, but we're going to have to prove it later. We're just going to assume it for the moment. So if console is a functor, then the solution of our problem is very easy. We get that, which allows us to write this implementation, and now we can finish with flatten. Flatten is easy enough. We have a chain of A. That's a sum type. We're going to deconstruct it. The done case, we have a chain of A, want a chain of A, literally nothing to do. We can just return that. And yeah, that moves around a bit, again, because we need a little more space. If we have that type that I'm not going to say out loud, we want to get to a chain of A. We have flatten, which does that. And I'm going to cheat again. We have next here, and we again, oops, sorry. We here have this rectangular shape. So clearly, we want something functorial. We want to be able to take that function at the bottom and lift it into console. Luckily, we are assuming that console is a functor. So we can do that. This is our solution, and we can now implement the entirety of the monad instance for chain, except for that one bit. Console needs to be a functor. So let's do that really quickly, because it's not at all interesting. We have map, console, the same type, bam. We have both branches. And in both cases, we have a function from something to A, a function from A to B, and we want to compose the two. The implementation is trivial. It's just function composition. The important thing to remember here, because that's going to come up if I manage to get to the end of that talk, is that console is a functor because of the continuation. The fact that console is a functor and that it has a continuation are very linked to each other. So that is an important thing to keep in mind. Right, now we get to write that, because, well, console is a functor, monad is a chain is a monad, right? Chain is a monad, console is a functor. And this is brilliant, isn't it? Because we now have that map. That means we can use syntax in the language, such as fault comprehensions. That's got a lot better. But if you remember, our code was dreadful, so much boilerplate. So let's try to solve that. And the way we solve that is by extracting atomic statements. What do I mean by that? Well, that here is the simplest possible read statement you can have. Read a string, return it. That's an atomic read. That's an atomic print, because all you do is print a string, return units. You cannot have a simpler print statement than that. So we're going to extract this into functions. First, print takes a string, does the rest. We can simplify the code here, a bit nicer. And we're going to do the same thing for read, extract it right here. Now, let's spend a little time looking at these two functions. It might not be obvious, but they're basically the same. So how do we see that? Well, both of them are a function from something to chain, executed within a console, and we want to get a console of chain. That is a rectangle, isn't it? We should be able to use something functorial here. And yeah, we can rewrite that code as a lift into console. We could do that. Now, you might argue this is actually worse. More code. True, it is, but also it allows us to spot a pattern. Because here, in both cases, we have a console of A, which we map into it and apply done, and we wrap the entire thing in the next. It's also the exact same function with a different input. So let's extract that function. I'm going to call it lift chain, and we can simplify the rest of the code to just be calls to that. Now, that's not necessarily super useful. It might not be clear why I have gone through the trouble of doing that. The reason I've done that is because this is a big hint that maybe chain is not that tied to console, because we were able to write print and read just in terms of lift chain, and lift chain merely needs console to be a functor. It doesn't need console to be a console. So there's a hint. There's something we might want to dig at in a few slides. Right, so now we have a atomic read statement. Well, that is nice, isn't it? It's not finished, though. Another pattern. We have this function that we execute within a chain of units in order to get a chain of string. That is a triangle. What did we say about triangles? Something flat mappy is going on. Yes, we can rewrite this entire thing as a flat map. And again, this looks worse. Yes, it does. But also that means we see that now, which is an atomic print. So we replace that with a print statement. And now all we have are nested maps and flat maps. This is so well supported by the language that we have dedicated syntax for it. I'm not going to take you through all the steps. Don't have the time, really. But the end result is that. And that is lovely, right? At least writing your program is lovely. You get to just write that, and it makes sense. You read that, it makes sense. Whatever the hell is going under the hood, who knows? But that makes sense. What have we learned? Please don't kill me. We can now write atomic console statements into it and lift them into a chain, which is brilliant. We decompose comfortably using standard fault comprehensions. We have also the intuition that it feels like maybe chain is not as tied to console as one might think. So, how do we explore that? How do we generalize chain? Well, we've seen that the monad instance didn't do anything about console aside from the fact that it was a functor. We also saw that lift chain only needed to be a functor. So let's take that intuition. Let's make chain parametric. We're not using console, we're using some type constructor f. And now we're going to add the functor constraint where needed. So here, this becomes parameter everywhere, and we need that to be a functor, so we add the constraint of functor. Same for chain. We're not taking a console, but an f. I'm going to rename that because it's not a console any longer. It wouldn't make sense. And we specialize print and read to a chain of console. And finally, we need f to be a functor. And that all compiles. What we have invented here is not, in fact, chain. What we've done is we created something, a construct, that if you give me a type constructor that happens to be a functor, I'll give you a monad for free. Where the name free comes from. This is the free monad over a functor, also known as free. We're not done with the renaming here. I want to show you something more. Done here takes an A, lifts it into our monad. That is exactly pure, isn't it? So that constructor is not called done, it's called pure. That constructor, next, right, takes nested f's, removes one layer of f. Have we seen that before? that happens to be flatten, so we're going to call that flatten. Interestingly, free now is exactly the defunctionalization of two functions, pure and flatten. And can I shut that down? I'm sorry. Pure and flatten, which are exactly the function that you have to write when you define monad in its most cumbersome configuration. And we have a dependency on a functor. So that is literally the defunctionalization of monad in its most cumbersome configuration. That would explain the statement that we had. A few boring talks, just doing the renaming for us. And now we fix program to be a free of console of unit. And I'm going to have to fix eval chain really quickly by just replacing the types. And, oh, no, I'm going too fast. Sorry, we're going to evaluate it now. So I'm replacing the types as we said. Console here becomes an F. That's merely going to be cosmetic. I'm just going to move that down because it makes the next step a lot easier. I'm going to do that and show you eval. Eval is the last thing that is specific to console here. We want to get rid of that. This is eval. For some parameter type A, takes a console of A and returns an A. Now we have A in both eval and eval chain. That is confusing. Let me rename that to X, right? So it's a function that given type parameter type X returns a console of X to X. That is exactly what this scalar free type allows us to write. And now we have a way of evaluating eval free. Okay, almost done. Now, I tend to be very annoyed by this fascination that the Scalar community has with, well, we don't like it when functions just return non-parametric values, don't we? It's got to be in some f, which is usually end up going to be either ID or IO. So why do we bother abstracting? I don't know, but we love doing it. So I tend to complain about that, but here it makes sense. We want to be able to encode the fact that this is effectful because, well, think about what we're doing. Console. We are reading from standard input, writing to standard output. That is very much global mutable states. So we're going to want to evaluate this entire thing into some type parameter J. And that's going to be really quick. It is, I swear. In the case of pure, we have an A. We want to return J of A. It's very straightforward. We know that, don't we? How to go from an A to a J of A. We need pure. So I'm going to make J into a monad. Technically, it merely needs to be an applicative, but I know it's going to be a monad very shortly. So, and then we have that type. I can't pronounce it, so you just read it. We want to get to a J of A, and then, well, we have this thing that looks vaguely triangularly shaped. Obviously, that is equal to flat map. So what we want to do is go from that to that. And if you call free of f of a just for fun x, we want to go from an f of x to a j of x. So we just fix handler to that. And now we have the free monad over a functor, and we got it. We know how to evaluate it. This is implementation. So what have we learned? We've learned that free, we have invented free, the free monad over a functor. And we found that it was very useful to compose arbitrary DSLs, provided they use continuations. So hang on, arbitrary DSLs. That sounds, that's not probably not what I should have written. Given one DSL, any DSL, if you encode it using continuations, you can chain it, and it allows you to compose elements of the DSL. That is what free is for. This is what we've done with console, isn't it? Now, the whole provided they use continuations, that is a huge provided, though, isn't it? We had to butcher that console type. I don't know about you, but I like my data types to be clear, concise. Console is not. That continuation is really awkward. It makes me really uncomfortable. So you might think, well, maybe there's a better solution out there. Maybe you've used the free implementation that you found in CAT and can't remember using continuations everywhere. And you'd be absolutely right. Here's the intuition. We have invented the free monad over a functor, and that involves continuations. But also, we've seen earlier, if you remember, I pointed it out, the fact that we have a continuation and a functor constraint are very linked. So maybe if we manage to invent the free monad over any type constructor, then we would not need a continuation. And yeah, that is a thing that exists. The free monad over a type constructor exists. It's called freer, presumably because it's slightly more free than free. And I know of two ways to get there. The first one is to have a bit of knowledge and to know that the free functor over a type constructor exists. It's called couneda, because why the hell not? And if you have a free monad over a functor and a free functor over a type constructor, maybe you can compose the two to get a free monad over a type constructor. Apparently that eventually pans out, I gave up halfway through because it's really, really very hard and a lot of work. What I did instead is solution 2, which requires a little bit more upfront thoughts, a little bit more intuition, but a lot less work. We have defunctionalized MONAD in its most cumbersome configuration, the one that has a functor requirement. How about we try to defunctionalize MONAD in its less cumbersome configuration, the one that doesn't have a functor constraint? Maybe we'll get somewhere. And yes, we'll immediately, very painlessly get to the free MONAD over a type constructor. I highly encourage you to run for that exercise. It's fun, you'll learn stuff, and I'd be very happy to see what you come up with. So if you do it, please hit me up on Twitter or whatever, and I'd be happy to look. In the meantime, I'd be happy to take questions, but yes, not here, out there, I know. And there's an article about this whole thing, so if you want to scan that, or it's on my blog. Thank you very much.
I do have one question.